The least value k for which a to the power k is congruent to 1 mod n is called the order of a mod n. If the greatest common divisor of a and n is 1, then the least value for which this is true must be a divisor of phi of n. We say that a is a primitive root if phi of n is the least power for which this is true. For example, let's see if 3 is a primitive root of 11. Since phi of 11 is 10, then 3 is primitive if 3 to the 10th is the least power congruent to 1 mod 11. Note that it doesn't actually do any good to evaluate 3 to the 10th, since this is guaranteed to be congruent to 1. What we want to know is if there's a lower power. Since the least k that will make 3 to k congruent to 1 mod 11 must be a divisor of 10, then k must be among, and if it's not 1, 2, or 5, it has to be 10. So we can check k equals 1, 2, or 5, and we check. So 3 is not a primitive root. Well, can we find a primitive root mod 11? So remember, a problem exists even if you don't know how to solve it. At this point, our best hope is trial and error. Fortunately, we don't have to go very far. So we can check 2 has order 1. Well, no, that's not true. But it could have order 2, 5, or 10, and we find. So the order isn't 2 or 5, and 2 to the 10th must be congruent to 1 mod 11, and so 2 has order phi of 11, so 2 is primitive. So let's see if we can find a primitive root mod something composite like 8. Since 8 is 2 to the 3rd, then phi of 8 is 4. So if an element A, where the greatest common divisor of A and 8 is 1, doesn't have degree 1 or 2, it will be primitive. So those numbers are the odd numbers, and so we find the squares, mod 8, and we get. So all elements relatively prime to 8 have order 2, and there are no primitive roots, mod 8. This leads to an important question. Given n, does a primitive root mod n exist? And if a primitive root exists, what is it? So again, a useful strategy is to start with primes. So suppose n is 2k plus 1 is an odd prime. Then for any a, because n is prime, a to the power 2k is definitely congruent to 1 mod n. Since a to the 2k is a squared to the power k, there's two possibilities. A squared is congruent to 1, so a has order 2, or a squared is not congruent to 1. Suppose a squared is not congruent to 1. Since a squared to the power k is congruent to 1, there are two possibilities. A squared has order k, or a squared does not have order k. So at this point, our reasoning is going to get a little complicated, so remember, concrete doesn't hurt. Suppose we're working mod 11. Then phi of 11 is 10. Now consider any value x. We know that x to the 10 is congruent to 1 mod 11, and so we can rewrite this. And so we have two possibilities. Either x squared is congruent to 1, so x has order 2, or x squared is not congruent to 1, so x squared has order 5. So a useful strategy in math and life, try to avoid things. So suppose x doesn't have order 2. If it has order 10, it's primitive root and we're done. But we want to avoid that, so assume it has order 5. So x to the 5th congruent to 1 mod 11. But since 11 is prime, Lagrange's theorem tells us this congruence has at most 5 solutions. So there's 10 values, mod 11, but 5 solutions are here, so there's at least one value that does not have order 5. Now if that element has order 10, we're done, so let's try to avoid that, and suppose that element has order 2. Now consider x an element of order 5, and y an element of order 2. What's the order of the product? It can't be 2 because if we square it, then y has order 2, so y squared is going to be congruent to 1, and we can ignore that factor, and so xy squared has to be x squared, which can't be 1 since x has order 5. And similarly, that product can't have order 5 because if we find xy to the 5th, we get, and this time x to the 5th is congruent to 1, so we can ignore that factor. And y has order 2, so this y to the 5th reduces down to y, which can't be 1 since y is supposed to have order 5. Finally, it can't be order 1, because if their product is congruent to 1, I can multiply by y to get, and since y has order 2, that y squared gives us a factor of 1, which we could ignore, and I have x congruent to y, but x and y have different orders, so they can't be congruent. So x can't be order 2, can't be order 5, can't be order 1, so it must be order 10, and so it's a primitive root. This suggests that if p is prime, there are always primitive roots mod p. Or does it? For p equals 11, phi of 11 is 10, that's 2 times 5, a product of primes. This allowed us to find an element y of order 2 and an element x of order 5. And since the greatest common divisor of 2 and 5 is 1, the product had to have order 10. But what if phi of p doesn't consist of a product of primes? We'll take a look at that next.